Hello everyone, I'm Deovrat Prasad and I'm here to talk about our recent paper which looks at environmental dependence of self-regulating agent feedback in massive galaxies. This work has been performed with Mark Voigt, Brian Say, and Forrest Glines at Michigan State University. As we all know, that agent feedback has emerged as a primary mechanism to control star formation rate in massive galaxies. However, the ability of agent feedback to self-regulate may depend on numerous environmental factors such as depth of the potential valve, the cesium pressure, and supernova sweeping due to presence of older stellar population. This work has been done to look at these environmental factors using numerical simulation. However, before we look at numerical simulation results, let's look at some of the theoretical arguments of how may these environmental factors play a role in controlling the feedback cycle. So if we assume that our galaxy has piecewise isothermal potential, then we can write the entropy and electron density profile as power law functions of radius. Now, for isothermal potential that is dominated by a stellar mass, as in case with our galaxies, the alpha is directly related to the ratio of a specific thermal energy of the ejected stellar mass to the depth of the potential well. This is assuming that the outflow is solely driven by SN1A heating. Now, for alpha of 2/3 at present SN1A rate, uh, what we arrive at is sigma v of about 240 kilometers per second. Now, this alpha of 2/3 is important because for alpha of 2/3, our electron density goes as 1 upon r. So our radiative cooling would go as 1 upon r square. On account of isothermal potential, our stellar mass density is already uh, has already dependence of 1 upon r square. So the SN1A heating rate would go as 1 upon r square. Now, this is very interesting because if alpha is less than 2/3, then our ratio of stellar heating to radiative cooling would decrease with radius. While for alpha of greater than 2/3, the ratio of stellar heating to radiative cooling would increase with radius. So I have performed a suite of numerical simulations with halo mass ranging from a few times 10 power 12 to a few times 10 power 14 solar mass with a spatial focus on a halo with M200 of about 4 into 10 power 13 solar mass. This halo has been initialized in such a way that for within R less than 10 kiloparsec, in one case sigma v is greater than 240 kilometers per second. In other cases, sigma v is less than 240 kilometers per second. And I have used ENSO code, which is a 3D hydrodynamic AMR code to run these simulations. If we allow the simulations to evolve over a few gigayears, what we find is in single phase galaxy where sigma v is greater than 240 kilometers per second, the system settles down in a steady state with constant low power jet outburst. This outburst is being fueled by precipitation of gas within 1 kpc because within this radius, the SN1A heating to cooling ratio is less than 1. Outside uh, outside 1 kpc, the SN1A heating dominates over radiative cooling and it does not allow any multi-phase gas formation, and there is no star formation in this case. On the other hand, in multi-phase galaxy with sigma v less than 240 kilometers per second, the agent power toggles between a high-powered state and a low-powered state. To start with, our simulation had the SN1A heating to cooling ratio of less than 1. It allowed for a lot of multi-phase gas formation and which funnel onto the supermassive black hole, fueling massive jet outbursts. This reduced the cesium pressure, allowing the SN1A heating to sweep a lot of matter into the cesium from the galaxy. Over time, the density in the circumgalactic medium built up and the radiative cooling overtook the SN1A heating again, and this resulted in the second massive jet outburst. So here are main findings of our paper. What we find is in massive galaxies with deep central potential and low cesium pressure, feedback mechanism is tightly self-regulating and permits only a small amount of multi-phase gas to accumulate and no star formation. In similar mass galaxies with shallower potential, feedback mechanism is more episodic and allows for extended multi-phase gas, and there is some episodic star formation. We find that agent feedback is critical in lifting the cesium pressure for supernova heating to be effective in massive galaxies. Please look at our paper, and if you have any questions, please email us. Thank you for listening. Thank you.